Hello and welcome to this final part where we'll just wrap up this discussion for single stage amplifier, which is chapter 3. And let us just quickly just go through this aspect that what is the need for degeneration. So I'll just quickly go through the expressions that we have derived, and we have seen that for a simple CH stage, the gain is this, diode connected, the gain is this, and so on and so forth, which you can already read. And we have already derived this, and for the degenerated case, we said that the gain is looking like this, right? And here we were saying that the gain is basically decreasing, right? Gain is decreasing because initially we had gain equal to GM times RD, but now the gain is GM times RD divided by this factor. So why are we using degeneration to begin with? What we must be able to appreciate is that this is a common problem in analog circuits, is the problem of process variation. That means that while fabricating the device, we can't ensure that all other devices have the same W or same L or same threshold voltage and so on and so forth. Which means that this process variation will also make our gain variable, right? So this is something that we don't, which is a big concern to us, not in single stage to be honest, but a bigger concern to us, especially when multiple transistors are considered concerned. Like for example, if one of the load is transistor and the common source is driving it, which is single stage only, but this is something which also like really troubles us in differential signaling. Another is the ambient variation that we see because we are already aware from semiconductor physics that mu and threshold voltage and all these terms vary with temperature, right? So this is also a big concern for us because, for example, if we see in this simple common source stage, we know that what happens basically is that first GM will vary with VGS, which is the input signal, right? So this means that GM is varying with the input signal, which is causing nonlinearity, right? So there will be certain nonlinearity. Also, not only that, but also if you are saying that V in a small signal, but still it is gonna cause some degree of nonlinearity, but also VT will also vary with temperature, which is again another concern, right? And then for diode connected device, we have expression of GM1 by GM2. So here you can kind of say that the variation in the VT can be compensated because its ratioing action is being observed here. But again, here still depends upon your V in, and this guy depends upon V out. So there is still some kind of nonlinearity to some degree, and the same argument can be extended to all of these guys, right? And this means that although the gain is decent enough, but there is a problem of variation, especially variation with input voltages or variation of the VGS across the concerned input stage or the concerned load stage, where the GM is essentially varying with signal. Right. So the idea is to have a gain which is not varying with the signal. And for that, one of the motivations to use degeneration that we can see below, because if we can approximate this expression, it becomes equals to minus RD by RS. Why? Because what I'm saying is that in the gain expression, this term is much, much greater than 1 and GMB is much, much less than GM. So I can approximate it as minus GM by GM by RS, right? And if I'm multiplying it by RD to get the gain, so I just get RD by RS, which is independent of GM, right? Which makes it kind of immune to signal variations. The gain is immune to signal variations, which is quite a good sign. So if I were to really summarize, the need for common source degeneration is to get immunity from signal AV immunity or AV immune from signal variation, which is basically GM, which was proportional to V overdrive, right? So that is the basic idea. Now let us just quickly discuss about about the large signal behavior of the common source. And so it is quite clear that till that Vin is equal to threshold voltage, the transistor is off, so there will be no drop across the load, and so our V out will be equal to VDD itself. Then, since we are increasing Vin further, but Vin minus VT or overdrive is still very, very small as compared to the output of the drain to source voltage, the transistor will be in saturation regime. And after the Vn crosses the VD sat mark, the transistor will go into triode regime, and thus we'll have this kind of a characteristic in large signal, right? So let us go and discuss about the source follower. So if we discuss about source follower, we have already discussed this expression for gain, and which is basically the buffer kind of characteristic, and the last signal behavior is also kind of like this, right? So here the transistor is in saturation, and eventually when V in is greater than VDD plus VT, which basically means it transits to triode, the buffering action will cease, and even intuitively, if you were to say if I'm keeping on increasing V in and I'm saying that it is a buffer action, but it can't, V out can't just surpass the supply voltage, right? So that is the one intuitive explanation behind that. So beyond this VDD plus VT point, the the output will kind of try to attain VDD where it is in triode regime and here it is in saturation regime. Also, we know that the buffer characteristic is not purely ideal and there is a certain gain which is gain which is less than one. So it is not like that the like ideal buffer character should be something like this, right? Where the slope was one, but we do observe that the buffering action is not that ideal, and the V out by V in ratio is a bit less than one, right? So this is the kind of characteristic which we'll observe in large signal, and why it won't just keep on going to infinity because eventually the device will transition to triode, with the condition which is given by that the gate voltage or the overdrive voltage basically is more than the drain voltage, right? So because the source terms will cancel out when you write the full equation. So that's the basic idea. And then talking about what will be the large signal behavior of the common gate amplifier. So here I have already drawn the circuit. So initially when V in is 0, the VB's value is such that the transistor is already in saturation, right? So the transistor is already in saturation, which means certain amount of current is flowing, which means certain amount of drop is there. So value will be clearly less than VDD. So let us say that it is at this particular point. And now as I increase my V in, my V overdrive, how will my V overdrive behave? See, V overdrive, let us say that even if I say that my VB is VDD, which is the maximum value that VB can typically go, this overdrive voltage will basically value. But uh, here my overdrive is VDD minus VT, which means that this guy this guy is probably greater than the drain to source voltage because huge current is already flowing because of saturation. So V out value is kind of low, which means that initially when V in is 0 and it starts to increase a bit, this drop, the overdrive voltage basically is more than drain to source overdrive voltage is basically greater than the drain voltage, right? And so initially here we'll find that the transistor is in triode regime. Okay, transistor is in triode regime, and as I will increase my V in, as I'll increase my V in, my current will decrease because my V overdrive is decreasing, and so my V out value will grow, and eventually a point will come that my V out value is high enough that my transistor now is in saturation regime, right? And when will that point come? That you can basically write over here that V out has to be greater than VB minus VT, right? Because here basically if you would have write that VDS and here you would have write VGS minus VT, so these two terms cancel out. That's why I'm saying again and again that you just have to check drain voltage with respect to the overdrive voltage, right? That's why, and overdrive voltage will be basically VGS minus VT, so I should better say VG minus VT. Saying it overdrive is not completely correct, but yeah. So after this point, it transitions to saturation, and since again I'm increasing my V in, which means that I'm still decreasing my current. So yeah, so my current again decreases sharply because the dependence on VGS is in the square form, and eventually my transistor becomes off. And when does it become off? When my Vin is equals to what? When my Vin is equals to what? So again, this point of transition also is incorrect. It should not be VB minus VT because here V at VB minus VT, my transistor will basically turn off, and so here it will become VDD. And at this particular voltage, this is some voltage at which the transistors V out basically, or here you can basically indicate that here V out is basically greater than VB minus VT. And so here it is in saturation, and here it is basically off. And so the V out value is VDD. So this is the kind of the last signal behavior that you will expect in CG stage. And now let us just move on to cascode, right? We already discussed the basic properties of the cascode, that the gain is of this order, which is basically GMR naught square, and R out is basically of this order. And so what will be the last signal behavior if you were to talk about it? So here the circuit is a bit shabby, so I'll just draw it again. And here you have your V in, and here you have your VB. Here I have some circuitry, and here I have my V out. So the idea is that initially when my Vin is 0, the transistor is off, which means that this transistor off, which means this transistor off, because no current can flow, which means that here it will just, here the pull-up circuit is connected to VDD, and so V out will also start at VDD, right? And here, let us say that this transistor is off. What is the marginal condition? See, this is a last signal analysis, and it's kind of an approximate analysis, right? So what is the maximum value that this guy Vx can have so that this transistor is off? That will be again Vb minus Vth. So that's why we have indicated that Vx value is Vb minus Vth. And so till the time this transistor M1 is on, which means that V in value is equals to Vt, both of the transistors will remain off. And after that, the transistor will get on. Now, when this transistor just gets on, we can observe just by inspection that that Vt minus Vt, which is the basically the Vg minus Vt, is less than Vb minus Vt, right? Provided that Vb value is high enough. So which means that this guy will transition into saturation, and since high current is flowing and high drop will be there, so V out value will fall, right? So this is what I'm plotting for V out. And if I were to plot for Vx, so since the current is increasing, which means that this gate to source drop must also increase. And again, Vb minus V out is less than V out, right? Because initially V out is equals to VDD. So which means that this transistor is also the M2 transistor will also be in saturation, and Vx has to decrease because the current is increasing, which means VGS has to increase, and so this guy will also be in saturation. Now here, two things are possible that I would want to emphasize. So here basically two things are possible. What can happen here is, now both of these guys are in saturation. What can now, any of the two things are possible. So I'll maybe I'll write it a bit below, that two things are possible. And I think my pen is a bit my pen is not that dark, so I think I'll just darken it. Yeah. So, okay, yeah, I'll just write it again, no issue. So, that basically what I'm trying to convey is that in this large signal model, two things are possible. And I think that since it is just revisions, you already know this, that two things are possible. And what are the two things possible? The two things that are possible is that either the transistor M2 can go out of saturation, or M1 can first go out of saturation, which means that either this guy can go in triode first, or this guy can go in triode first, right? They both can simultaneously also go into triode, but that is obviously not that much likely. So any of these two transistors will go into triode first, right? That is the basic idea. And how can that happen? M2 can go into triode first if V out value decreases so much that that it is now less than VB minus VT. This can typically be true when VB value is high enough, and so this transistor M2 can go out of saturation first. And now, since M2 is already out of saturation, so you can just say that, yeah, now it is in triode, and so Vx is also kind of decrease like this. Another thing that you can say is that M1 can also go into M1 can also go into, and yeah, if M2 goes into triode first, so V out will definitely go something like this, right? And if because the drain of M2 is V out, and M1 can go into triode first if VB minus VT, or I'm not sorry, that was the initial value. If Vx basically falls below V in minus VT, right? And So any of the two cases are possible, but nonetheless, the large signal behavior will typically kind of look like this only, that eventually a point will come when both transistors are in triode and they will kind of try to merge with each other. And here, which means that the which means basically that the V out and Vx value will kind of follow each other in triode. And this is the behavior in a triode, this is a behavior in saturation regime. And here, the two transistors are off. And that is the more or less the large signal behavior. And in folded also, you kind of see the similar behavior, right? And I'm not discussing this in detail because it is more or less the same thing. And telescopic or this kind of cascode configuration you basically use for high gain, and this is also used for high gain. But the path consumption is more, as you can see, because we need two current sources to bias it properly. Whereas here we could have gotten away with one bias media, right? And that's the basic idea about it. And here output swing is not that great, but in folded cascode, we see that the output swing is also kind of good. And we'll be able to appreciate the differences and the benefits and the disadvantages better when we will actually discuss op-amp later on. Here I have just written something about shielding property. That is the intuitive idea behind how the shielding works is that, for example, this is a cascode that we can clearly see. And so if there is some variation at this node voltage at V out, since this resistance effectively is very much high, we know intuitively that if the resistance value is too large and I have some del V across it, some del V swing, then del V by R, the del I current will also be very small. And since del I current is very much small and very small del I current will flow here, Vx will also very marginally, right? And that's the basic idea about shielding, that the variation of output won't translate to variation at node Vx. And this property is something that we utilize in current mirror, which I have drawn. And it's a bit simple current mirror where we are basically utilizing cascode to make this voltage equal to this voltage, right? So that we can basically eliminate the effect of channel length modulation, something which we'll discuss later on. And this is the example also one is given in Razavi book, that by using the shielding property of cascode, you can also reduce the mismatch in differential configuration circuits. And so this is something that again you can see the example in book itself, and the idea is pretty much the same. And if I were to just quantify it, the idea here is that if there is a del V potential difference between the drains of M1 and M2, then the current difference will also be proportional to what? Del V times lambda, right? And I think you can easily imagine that if you just write the two currents equation down, and you can just see that one of the currents is greater by this margin, since it is since the currents are proportional to 1 plus VDS times lambda. So this is the difference that we'll observe, and the difference will be proportional to this guy. And what will happen for a cascode when we are basically applying cascoding is that if I am biasing these two guys, so this del V voltage, let us say that here the reference voltage is VDS and here it is VDS plus del V. So if you just apply the small signal analysis, which means basically you are assuming the trans to be in saturation, the effective resistance that this guy will see from output will be what? Just, let us just try to write the intuitive expression, that is just Gm R naught square, right? And that means that the current flowing because of this del V will be del V divided by Gm R naught square. And in small signal, this guy is grounded, this guy is grounded, which means that current can only flow through this R naught path, right? Which means that the change in this node voltage, right? If I'm calling it Vp and I'm calling it Vq, the change Vpq will be given by the small signal current flowing due to del V times this resistor, right? So that is R naught. And now we can just say that this is basically equal to del V by Gm R naught. And this means that the change in current in these two branches will then be proportional to del V Gm R naught, right? Times lambda. So we can observe that in the two cases, the current difference is greatly reduced, right? Because it is reduced here by a factor of gm r naught, which will be great, which will be a bit, the term in the example in Razavi is a bit different, because here he has done the exact analysis and here we are just doing the intuitive analysis. But that is the basic idea, that by using cascoding, the mismatch is significantly reduced. And that was the basic idea over here. Okay. And So I think one more thing that is worthy to mention is that this shielding property of Cascode and all these great properties that are basically discussing, it is true only for saturation mode of operation, because once it falls out of saturation, this great shielding property, high output impedance and all is not that much there, right? And so we must always bear in mind that is also why I decided to revise the last signal behavior also, that all these great properties that we are discussing is only true when the transistor is in saturation regime. Yes, we can also utilize it in triode, subthreshold, all that, but you should always know the context as in what region is your device operating, and then we can comment on all these wonderful things. And I think with this, our revision of chapter 3 is complete. And that being said, I think I'll make another video for revision of chapter 4 and 5. And this basically wraps up our chapter 3. And this was a great revision for me, especially. And if anyone was watching, thanks for watching. And I hope that you could also benefit a bit from this. If not, well enough. And if you were able to find any problems or any errors that I did while discussing all of this, please feel free to correct me. I'll be very much grateful to you, and I'm up for discussion too on such kind of topics. So again, thanks for watching, and I'll see you in the next video.